right? You're exhaling. You want to make sure the blood is going by at the right speed to get the carbon dioxide out. So you always want to coordinate how fast your blood is flowing with how fast you're breathing. Right? So they need to interact together. Okay. All right. So let's say now we've successfully transferred our oxygen into our blood. What's the main way you carry oxygen in your blood?
Hemoglobin.
Iron.
Through hemoglobin, through iron, and that's all in the red blood cell. Your main job of the red blood cell is to transport oxygen. So red blood cells are just carriers of oxygen. So the majority of your oxygen that you put into your blood, you specifically want it to bind to the red blood cell. And how it binds to the red blood cell, if you take a generic red blood cell, and if you were to zoom in, you'll see lots of these proteins called hemoglobin. So one red blood cell is going to have millions of these hemoglobin proteins. The importance about the hemoglobin protein is that the hemoglobin protein has to have an iron on it. The reason why it has to have the iron, which is this little green dot, is because it's actually the iron that physically bonds to the oxygen. Right? So that's why they say, oh, you need iron for your blood, right? Because you need iron to make up your red blood cells. Without the iron, the red blood cells won't bind and carry oxygen. Right? They can't do their job. Okay? So that's, again, how oxygen is transported. So that's why you need the iron in your diet. All right. Carbon dioxide is a little different. Sorry, ignore this down here for now. Carbon dioxide has actually multiple ways it can be carried in the blood. Whereas oxygen is just strictly bound to red blood cells. Carbon dioxide has 3 methods. So one is carbon dioxide can actually just go into the blood plasma and just be transported as CO2 as itself. That's not the majority of the way it's carried. Only about 10% of carbon dioxide is carried in the plasma. But again, you don't have to do anything. You just put the CO2 in the plasma and it just goes in the blood. The second way is carbon dioxide actually can also bind to hemoglobin. So if your red blood cell is not carrying oxygen, it has the opportunity to actually pick up carbon dioxide and transport that. Again, the majority of your carbon dioxide is not transported this way. Probably only about 20% of your carbon dioxide goes on hemoglobin on a red blood cell. The third option is called the bicarbonate ion. And this is how the majority of your carbon dioxide is transported, about 70% of your carbon dioxide. And let me explain how it works. When you put carbon dioxide in water, and remember, blood plasma is mostly water, right? So when you combine carbon dioxide and water, it makes this compound called H2CO3, or bicarbonate acid. And what this does is it will dissociate into a proton, right, which is the hydrogen with the positive charge, and HCO3 with the negative charge. This one over here, this is the bicarbonate ion. So notice hidden in there is the CO2. So this is your most common way you transport carbon dioxide. But notice, when you transport carbon dioxide as a bicarbonate ion, you also make proton. What's the effect on protons with acidity? How are protons and acids related?
Increases acidity.
Increases acidity, right? The more protons you have, the more acidic a solution is. Right? So let's think about that. If I have more protons, my blood actually gets more acidic. Do you guys remember what's a good pH level for your blood?
7.5.
Roughly 7.4, right? Give or take a little bit. So 7.35 to 7.45 is appropriate. If I start having too many protons, right, my acidity is going to go up. What happens to my pH? Does it go up or down?
The number goes down.
Remember, the more acidic you are you closer to 1 on the pH scale, or are you closer to 14?
200.
Yeah, remember the pH scale? 1 is extremely acidic, like hydrochloric acid. 14 is extremely basic, like bleach. So if I have more protons, right, so more CO2 I have in my blood, the more protons I have in my blood. The more protons I have in my blood, the more acidic my blood is, which means the pH of my blood is going to go down. So instead of being at 7.4, it might start dropping, 7.35, right? Or go down maybe into 7.3. So notice this is a problem. Right? We want to be very careful about the acidity in our blood. So a lot of times we're so focused on breathing and say, yes, we need oxygen for energy, and that's true. Right? But equally important is to make sure you get rid of your carbon dioxide. If you don't have the right level of carbon dioxide in your blood, it's going to throw your pH balance off. Right? And then that can have effects on your blood pH, which can affect your whole body. So you want to be careful. You want to be breathing in the oxygen, but you also need to make sure you exhale the CO2. Okay.
So all this is happening
Maybe that's
in the blood plasma?
ventilating is
Yes.
bad.
Yeah, so this whole conversion is in the blood plasma because that's where all your water is. Yeah. So again, in the blood plasma, yes, you'll have just some straight up CO2 molecule, but mostly it's going to be HCO3 with a negative charge.
Do you also filter out that through your urine?
So once you get to the lungs, this converts back to CO2 and then you exhale the CO2.
Oh, okay.
Because then when you get to your lungs, you don't have the water anymore. All right. Okay, so again, be very careful about your CO2 levels in your blood because if you don't balance your CO2, you could have loss of your blood pH.
So then it has to, there's like a phase transition where it turns to gas?
Yep, so when you get back to that respiratory zone,
Mhm.
right, that's where you then convert the bicarbonate ion back to the CO2 gas and then exhale that.
Doesn't that require like a lot of energy? Doesn't that require like a lot of energy to turn it from liquid to gas?
It's all based on the concentration
Mm.
and whether the liquid or in the pressure. So it's all like the chemistry behind it makes it favorable to switch back once you get to the respiratory zone where there's a higher concentration of gas.
Cool.
All right. Okay, so when it comes to regulation of breathing, one thing we have to be careful about is our carbon dioxide. So, for example, this is why hyperventilation is actually really problematic. So first of all, what does it mean to hyperventilate? What happens to your breathing rate?
Breathing too
It increases, right? Hyper is just too much. So you see someone hyperventilate, you right? They're breathing really, really hard, really fast. All right. Does anyone know if someone's hyperventilating, what you might do as a quick fix?
paper bag.
Yeah, you see people breathing into a brown paper bag, right? So we're going to try and understand why is it beneficial if someone's hyperventilating to have them breathe into that brown paper bag. Well, let's figure out what the problem is first. If you're hyperventilating, right, you've got basically signals from the brain telling your muscles to move too quickly, right? So you're breathing in and out too fast, which means if you're breathing in and out too fast, think about you're breathing out a lot. You're actually losing a lot of the carbon dioxide, right? You're exhaling too often, so your carbon dioxide is leaving your body. And again, that's not good. What happens is, because you're breathing too fast, you lose carbon dioxide. So to fix that, of course, you want to slow down your ventilation and you want to slow down your breathing. Now, when you breathe into a paper bag, what are you breathing into that bag? What's being exhaled? The carbon dioxide. Again, if you lose too much carbon dioxide, it's going to throw off your pH balance. So, when you inhale, what are you breathing back in? That carbon dioxide. Yep. So, the whole goal of breathing into the paper bag has nothing to do with oxygen. It actually has to do with regulating your carbon dioxide because you breathe back in that carbon dioxide you lost. So it helps you balance the carbon dioxide in your blood, therefore balancing your blood pH. Okay. Any questions on that?
But in hyperventilation, you're breathing out, but you're breathing into, so why is the ratio of oxygen to CO2 messed up? Because you're doing a one-to-one.
Right, so the problem is you're still short on oxygen. So the question is why you're still doing the one-to-one, right? You're still breathing in too little or too fast also, right?
Right.
So there's no issue if you breathe in too much oxygen.
Right.
Right? That's not a problem. But there is an issue if you breathe out too much carbon dioxide.
Oh, okay.
Right? So that's why you bring in the brown paper bag. And if you bring in the brown paper bag, of course you're not going to be getting as much oxygen anymore. But your immediate problem is you're exhaling too much carbon dioxide.
The pH level of your blood.
Yep. So again, hyperventilating, if you breathe in too much, no worries about breathing in too much oxygen.
And that this differs from really high intense exercise activity because because oxygen is actually needed because you're in oxygen debt.
Yeah, when you're doing high intense activity, you're breathing a lot too,
Yeah.
right? But again, the reason why you're breathing a lot in that case is because you're trying to get more oxygen into your body to repay the oxygen debt, right? Again, of course, it's still not good to be in that condition for too long either because you would be losing a lot of CO2 at the same time. Yep. But it's depending on what is your body's need. Hyperventilating is an extreme form, right? It's more even faster breathing than like when you're exercising.
Piggybacking on Rajan's question, if you do intense exercise, do you also produce more carbon dioxide?
Yeah, great question. So Rachel asked, if you do very intense exercise, you start breathing heavier because you need more oxygen for energy, right? Does that mean you also make more carbon dioxide? Yeah, right? Because the whole process of using the oxygen for energy is cell respiration. So the more cell respiration you do, of course, one of the byproducts is carbon dioxide release. So the more oxygen you breathe in for energy, the more carbon dioxide you're going to need to exhale.
In what circumstances would you be intaking too much carbon dioxide?
Oh, intaking too much carbon dioxide. Yeah, so that's right. So in this case, you're just trying to get back the carbon dioxide you lost, right? But you can imagine if you were in an atmospheric condition where there's too much carbon dioxide, and when you inhale, you're inhaling carbon dioxide more than what you need, then that would be also detrimental. So I don't know exactly like what environments would it be ones that would have too much carbon dioxide, but that would be kind of, there's like carbon monoxide poisoning, but I could imagine there'd be a similar like carbon dioxide poisoning if you were in a place that was just loaded with carbon dioxide. But yeah, but in the usual atmosphere, right, there's not a high amount of carbon dioxide in tanks.
Is carbon dioxide also a byproduct of fuel?
Right, so carbon dioxide is that also a byproduct of fuel. Right, there's all the carbon dioxide emissions, right, which is leading into the atmosphere. So if you're near like a factory plant that was releasing a lot of carbon dioxide emissions, then that could be a problem. Yeah, great question. All right, so lastly, let's look at some respiratory areas that control breathing. So what do we always say about the brainstem? What's the main function of your brainstem?
Survival.
Survival, right? And what are the things we need to survive? Breathing and heart pumping, right? So we already discussed how the brainstem has cardiovascular centers in it, right? Centers that increase heart rate or slow down heart rate, vasomotor centers that increase or decrease blood vessel size. So we talked about brainstem having important areas to regulate cardiovascular system. It shouldn't be any surprise that the brainstem also have areas that regulate your respiration. So if you were to look at the brainstem, remember the brainstem consists of three major parts. We have the midbrain at the top, the pons in the middle, and the medulla down at the bottom, which merges with the spinal cord. So if you look at the medulla, which again is at the more inferior part of the brainstem, there is a rhythmicity center. And what this center does is it regulates your automatic breathing rhythm. So as you guys sit here, you don't have to think about breathing, right? You just naturally breathe in and out at rest. And that's again because in the medulla down here, there is a group of neurons that automatically send out nerve impulses to your muscles to tell you to breathe in, and then relaxes them to breathe out. But you guys know that your rhythm of your breathing can change. For example, when you go to sleep, what happens to your breathing?
Slow down.
It's naturally slows down, right? Or if you start running, what happens to your breathing rhythm? It naturally increases. So in addition to the medulla, in the pons, so right superior, there are centers that actually change your natural breathing rhythm. So they can either stimulate it, for example, when you run or exercise to make you breathe faster, or they can inhibit the inspiration and expiration. So like when you go to sleep, then your breathing slows down. So again, in the medulla, you have like your standard rest rhythm rate, and then in your pons, you can override that according to the condition that you're in. All right. So that wraps up respiratory system. So we know now that we have gas exchange in the lung that occurs at the structure called the respiratory membrane, and it's controlled by the pressure of gases, high to low. And we also know that oxygen and carbon dioxide are transported by blood and ultimately can affect the pH. And then finally, breathing is controlled by respiratory areas in the medulla and the pons, and both are in the brainstem. Okay, so that's the end of respiration. Next, we're gonna get